Now let us get into the third topic of induction and recursion, that is recursive definitions and structural induction. Now, this topic is divided into four parts. The first part, recursively defined functions. Under this, you will learn the definition of recursive functions, few examples, Fibonacci numbers, and Lim's theorem. In the second part, recursively defined sets and structures. Here you'll learn recursive definition for sets, strings, string operations, proposition logic, trees, etc. The third part, structural induction, includes what it is, when it can be used, what are the steps involved in structural induction, few examples to illustrate the application of structural induction. The fourth part, generalized induction. Here you will be learning where it can be used, how to apply it, example to illustrate the application of generalized induction. My dear students, if you are asked to define an object, sometimes you feel it difficult to define this object explicitly. But given a chance to define this object in terms of itself, probably you can define that object. This process of defining an object in terms of itself is called as recursion. Now let us see the definition for a recursive or inductive definition of a function. This consists of two steps. The first step is basis step, which specifies the value of the function at 0. Sometimes it can be other than 0 also. Recursive step, it gives a rule for finding its current value at an integer from its values at smaller integers. So here probably if you want to find out a function of n that will be expressed in terms of function of n minus 1 or a function of n minus 1 and n minus 2 and so on. So in recursive step, the functional value at an higher integer is expressed in terms of the function value at lower integers. A function f of n from the set of non-negative integers to the set of real numbers will be expressed as a sequence a0, a1, so on, where ai is a real number for every non-negative integer I, that is f of I is equal to ai. In the first example, the function f is defined as f of 0 is equal to 3, that is the basis step, and f of n plus 1 is equal to 2 into f of n plus 3, which is a recursive step. Here you can observe that the function value at n plus 1 is expressed as the function values at lower values. Now we have to find f of 1, f of 2, f of 3 and f of 4. For f of 1, it is equal to 2 into f of 0 plus 3. F of 0 value we have from the basis step, which is 3. You substitute here 2 into 3 is 6 plus 3 is equal to 9. For f of 2, which is equal to 2 into f of 1 plus 3. f of 1 value we get from the previous step, which is equal to 9. Substitute it here and you'll get 2 into 9 plus 3 is equal to 21. Similarly, you can find the values for f of 3 and f of 4. In the next example, a recursive definition for the factorial function n factorial has to be defined. As all of you remember that the definition includes two parts, that is basis step and recursive step. Basis step will give the value of the function at value 0. So 0 factorial is 1. So we define f of 0 is equal to 1. And you also know that the function value at any value will be given as that value into the function value at the previous one. So f of n plus 1 is equal to n plus 1 into f of n, which gives us the recursive step. Let us take one more example to give a recursive definition for sigma k is equal to 0 to n ak. So here also the solution should have two parts, that is basis part and recursive part. The basis part will take the k at the value 0. So sigma k is equal to 0 to 0. Ak will give us a0. The second part is recursive part, where we'll be defining the value at n plus 1 in terms of n. Here sigma k ranges from 0 to n plus 1 ak is equal to sigma k is equal to 0 to n ak plus a n plus 1 will give us the recursive step for this recursive function. These Fibonacci numbers are introduced by a person named as Filius Bonacci and popularly known as Fibonacci. He is an Italian merchant, extensively traveled through Mid East. He introduced this series based on a rabbit problem, which we are going to study in later chapters. He also wrote books on geometry and trigonometry. Now let us see how these Fibonacci numbers are defined. Here the basis step includes two things, f0 which is equal to 0 and f1 equal to 1. And the recursive step is defined as fn is equal to fn minus 1 plus fn minus 2. That is, the nth Fibonacci number is obtained by the addition of n minus 1th Fibonacci number and n minus 2th Fibonacci number. Find f2, f3, f4 and f5. And the solution, we find f2 by the addition of f1 and f0, that is 1 plus 0 is equal to 1. f3 by adding f2 and f1, that is 1 plus 1 equal to 2. f4 similarly by adding f3 and f2, and finally f5 by adding f4 and f3. My dear students, this proof is very important, so you listen carefully and understand completely because it involves few basics from mathematics and it is useful in proving the next theorem, namely Lem's theorem. Now let us get it into the proof. show that whenever n is greater than or equal to 3, Fn is greater than alpha to the power of n minus 2, where alpha value is given as 1 plus root 5 whole divided by 2. Here you might be confusing what is Fn. Fn is the nth Fibonacci number where n values will be taken as greater than or equal to 3. Now let us get it into the solution. Let P of n be the statement Fn greater than alpha to the power of n minus 2. In order to prove this, let us use strong induction with n values greater than or equal to 2. In the basis step, P of 3 holds since alpha is less than 2. This 2 is equal to your third Fibonacci number. That is F3 will be 2, starting from F0 is equal to 0, F1 is equal to 1, F2 is equal to 1, so F3 will be 2. Now when it comes to the alpha value, it is 1 plus root 5 whole divided by 2. Root 5 value is 2.236. So 1 plus 2.236 will become 3.236 divided by 2, whose value is less than 2. Now let us check for P of 4. This also holds since alpha square is equal to 3 plus root 5 whole divided by 2 is less than 3. Here also it is 3 plus 2.236, which is 5.236 divided by 2, which is less than 3, that is, which is less than fourth Fibonacci number F4. Now you have to understand how you got this alpha square as 3 plus root 5 whole by 2. You perform the calculation of 1 plus root 5 whole square divided by 2 square, and when you expand it, 1 plus root 5 whole square, it is a square plus b square plus 2ab, which comes to 1 plus 5 plus 2 into 1 into root 5 divided by 2 square, that is 4, which will be equivalent to 6 plus 2 root 5 divided by 4. Take 2 common out, it will become 2 into 3 plus root 5 divided by 4. You cancel out 2's, so it finally results in 3 plus root 5 by 2. That is how you got alpha square value as. Now let us get into the inductive step. Assume that P of j holds, that is Fj is greater than alpha to the power of j minus 2 for all j values ranging from 3 to k, where k value is taken as greater than or equal to 4. Now we have to show that it also holds for P of k plus 1, that is Fk plus 1 is greater than alpha of k minus 1. Here alpha, what we have taken it as 1 plus root 5 whole divided by 2, is one of the roots for the equation x square minus x minus 1 equal to 0. This you can check by using the formula for finding the roots, that is minus b plus or minus root of b square minus 4ac divided by 2a, with the values of a is equal to 1, b is equal to minus 1, and c is equal to minus 1. When you find out the value for minus b plus root of b square minus 4ac by 2a, Then you'll get the alpha value as 1 plus root 5 whole divided by 2. Now, x square is equal to alpha plus 1. Now, how to prove this? Alpha square, we got it as 3 plus root 5 whole divided by 2. Now you substitute alpha value into alpha plus 1. This becomes 1 plus root 5 by 2 plus 1. When you solve it, it becomes 1 plus root 5 plus 2 whole divided by 2, which is equal to 3 plus root 5 by 2. Hence, alpha square is equal to alpha plus 1. Now we have fk plus 1 greater than alpha to the power of k minus 1. Now let us try to solve this. Alpha to the power of k minus 1 can be expressed as alpha square into alpha to the power of k minus 3. Now alpha square can be substituted with alpha plus 1. Hence it becomes alpha plus 1 into alpha to the power of k minus 3. When you expand it, it becomes alpha into alpha to the power of k minus 3 plus 1 into alpha to the power of k minus 3. When you simplify it, alpha into alpha to the power of k minus 3 will become alpha to the power of k minus 2 and then plus alpha to the power of k minus 3. By the inductive hypothesis, because k is greater than or equal to 4, fk minus 1 will be greater than alpha to the power of k minus 3. Similarly, fk will be greater than alpha to the power of k minus 2. So now we can express f of k plus 1 is equal to f of k plus f of k minus 1. You substitute fk with alpha to the power of k minus 2 and you substitute fk minus 1 with alpha to the power of k minus 3. And just now we have shown that alpha to the power of k minus 2 plus alpha to the power of k minus 3 is equal to alpha to the power of k minus 1. Hence, fk plus 1 is greater than alpha to the power of k minus 1. That is, p of k plus 1 holds. Lam's theorem is because of Gabriel Lame. He contributed significantly to number theory, applied mathematics, and thermodynamics. This theorem states that let a and b be two positive integers with a property a greater than or equal to b. Then the number of divisions used by the Euclidean algorithm to find GCD of a comma b is less than or equal to 5 times the number of decimal digits in b. My dear students, what my sincere suggestion is, in order to prove this theorem, you should have a clear understanding of Euclidean algorithm. If you have not came across or you forgot about it, you just pause this video and learn Euclidean algorithm before getting into this proof. Now let us proceed with the proof. When Euclidean algorithm is used to find GCD of a comma b, where A is greater than or equal to B, n divisions are used to obtain greatest common divisor. We start with A is equal to R0 and B is equal to R1. How it proceeds is we call with GCD of R0 comma R1. In the next step, it will be called with the GCD of R1 comma the remainder of R0 dividing with R1 and then GCD of R2 with the remainder of R1 dividing with R2, so on. Now this process is expressed as like this. R0 is equal to R1 into Q1 plus R2. That is R0 is expressed as Q1 times of R1 plus R2. So here R2 is the remainder. So R2 values lies between 0 to R1 minus 1. It can't be equal to R1. Similarly, R1 will be expressed as R2 times Q2 plus R3, that is R3 is a remainder here. Similarly, Rn minus 2 is expressed as Qn minus 1 times of Rn minus 1 plus Rn. Finally, Rn minus 1 is expressed as Rn into Qn and our Rn will be the greatest common divisor. Before proceeding with the current slide, my dear student, just go back to the previous slide and note down those equations. It starts from R naught equal to R1 Q1 plus R2 till to the Rn minus 1 is equal to Rn into Qn. This topic explanation we start with. We have taken the coefficients Q1, Q2, so on up to Qn minus 1 are all at least 1. That is, they can be 1 or greater than 1. This you have to keep it in mind. Moreover, we'll take the last coefficient Qn is greater than or equal to 2 because it has to be at least 2. Now with this, let us proceed. We have taken Rn as the greatest common divisor. The greatest common divisor can be 1 or greater than 1. So Rn will be greater than or equal to 1. This 1 is equal to our second Fibonacci number, that is F2. So Rn is greater than or equal to F2. Now let us come to Rn minus 1. Rn minus 1 is equal to Rn into Qn. But we have taken Qn value greater than or equal to 2. So Rn minus 1 will be greater than or equal to 2 into Rn, which is greater than or equal to 2 into F2 because Rn is greater than or equal to F2, which is equal to F3. So Rn minus 1 is greater than or equal to F3. Now let us take the equation for Rn minus 2. Rn minus 2, we expressed it as Rn minus 1 into Qn minus 1 plus Rn. We have taken Qn minus 1 value as at least 1. So when you substitute 1 in the place of Qn minus 1, Rn minus 2 will be greater than or equal to Rn minus 1 plus Rn. Now, in the place of Rn minus 1, since it will be greater than or equal to F3, you substitute F3. In the case of Rn, because it is greater than or equal to F2, you substitute F2. F3 plus F2 is equal to F4 as per our Fibonacci series. So Rn minus 2 will be greater than or equal to F4. Similarly, when you proceed, R2 will be greater than or equal to Fn, and finally B, which we have taken it as a R1, will be greater than or equal to R2 plus R3, which will be greater than or equal to Fn plus Fn minus 1, which will be equal to Fn plus 1. I hope it is clear to all you people now. So B will be greater than or equal to Fn plus 1. So when we use n divisions by the Euclidean algorithm to find GCD of A comma B, where A is greater than or equal to B, then B will be greater than or equal to Fn plus 1. From the previous example, we have already proved that Fn plus 1 will be greater than alpha to the power of n minus 1 for all n greater than 2, where alpha is equal to 1 plus root 5 by 2. Now, when you substitute that there here, B will be greater than alpha to the power of n minus 1. We all know that alpha is equal to 1 plus root 5 whole divided by 2. When you find out the value of log alpha base 10, it approximately comes to 0.208, which is greater than 1 by 5, because 1 by 5 is 0.2. With the conclusion from the previous example, we found out that B is greater than alpha to the power of n minus 1. This we have done in the previous slide. Now you take log on both sides. It becomes log B base 10 is greater than log alpha to the power of n minus 1 base 10. When you simplify it, it will be log B base 10 greater than n minus 1 into log alpha base 10. In the previous step, we saw that log alpha base 10 is greater than 1 by 5. When you substitute it, it becomes greater than n minus 1 divided by 5. That is, log B base 10 is greater than n minus 1 divided by 5. When you simplify it, n minus 1 will be less than 5 into log B base 10. Now, let us assume that B has k decimal digits. Then obviously B will be less than 10 to the power of k. For example, if B is having 3 decimal digits, then the maximum value it can take is 999, which will be less than 10 cube. Now, for B less than 10 to the power of k, you take log on both the sides. It becomes log B base 10 less than log 10 to the power of k base 10, which finally becomes log b base 10 less than k. Now it follows that we can substitute with n minus 1 less than 5k, because in the place of k we can go with log b base 10. Since k is an integer, n will be less than or equal to 5k. Here what is n? N is the number of divisions that we have performed in order to find out GCD of A comma B. As a consequence of Lam's theorem, big O of log B divisions are used by the Euclidean algorithm to find GCD of A comma B whenever A is greater than B. Now let us check it out. By Lam's theorem, the number of divisions needed to find GCD of A comma B with A greater than B is less than or equal to 5 times of log B base 10 plus 1. Why is this? Because since the number of decimal digits in B is equal to log B base 10 rounded down plus 1 is less than or equal to log B plus 1. Hence, the Lam's theorem is proved. And Lam's theorem was the first result in computational complexity.